greater than the Zener potential, then my diode is conducting, so diode is on. And the voltage across the diode will be fixed at Vz, the Zener potential. If that voltage turns out to be lower than the Zener potential, then my diode is off. So my diode becomes an open circuit, and the resulting circuit becomes exactly like solving any other uh, circuit with a resistor and a voltage source. Okay, so let's try to put them. We already did one example. Let's do another example here. So here is a question. You have been given a voltage regulator circuit. So in the exam, you may not be told that it's a voltage regulator. It's basically a circuit. And I want to find out what is the, find out several parameters. I want to find out what is the load voltage. The load voltage is this voltage. I want to find out what is VR. VR is the voltage across this resistor, this resistor. I want to find out VL. I want to find out VR. I also want to find out IZ. What is IZ? IZ is Zener current. So sometimes in the question, if you don't see what IZ is defined properly, but you see that find IZ, that means it's clear you are looking at a Zener diode and you want to find the current through the Zener diode. And finally, you have something called PZ. What is PZ? PZ is the power dissipated. So we discussed this in the last class. We said that power PZ is the power dissipated by the Zener diode. What is power dissipated? There are many ways to find out the power dissipation.
It's just the second match, and even the last match we got that bowling, we won that match.
Way we do it over here is you can see the simplest way to do this is you take the voltage across the Zener diode, multiply that by the current flowing through the Zener diode, that is the power. So we are asked to find these four parameters: VL, VR, IZ, PZ. So how do we go about this? As usual, the first step is to check for the condition of the diode. Is it on or is it off? On means it has reached the Zener potential. So the Zener diode would always be reverse biased. So assuming it's the reverse bias diode, have I reached the Zener potential or have I not? So that's the first question. And how do I find that? For that, I just remove the Zener diode from the circuit. So I remove this diode from the circuit. So I remove it from the circuit, and when I remove it, I get a circuit like this. So this thing. So now my terminals A and B, I had written down A and B here as well in the original circuit as well, A and B. So I remove the Zener diode and I get the these two terminals, open circuit terminals, and I want to find out what is the voltage across these two terminals. So for that, we already know how to do that. That voltage V is what? That voltage V is equal to the voltage across this resistor, 1.2 kilo ohm road resistor, right? So the voltage across A and B would be the same as the voltage across 1.2 kilo ohm. So that's a property of any parallel connection. So if you have two parallel, in any circuit, if you have something here, let's suppose let's draw it a little better. So any circuit, if you have something like this, let's suppose, I don't know what it is, I'm just drawing it arbitrarily. So now I have some diode, some Zener diode, I don't care what it is, and something, I don't care what it is. But the point is, the voltage across these 2 points would be the same as the voltage across these 2 points. So the voltage here, whatever voltage you see, this is V1, and whatever voltage you see, V2, these two will always be the same. Why? Because although we are drawing the circuit diagram in a way that looks, I mean, it may not be straightforward for some people to see this, but the point is that these things is actually the same point. We just have a conductor in there. So what I really had was something like this. So this. So basically these 2 points, this point A is just this point A. These 2 points, this point B is just this point B. Okay, so that means that whenever you have a parallel configuration like this, the voltage across one parallel branch is the same as the voltage across the other parallel branch. So we don't really need to. So when you are asked to find out the voltage across A and B, then all I need to actually find out is the voltage across the load. That's all. But of course, that's not true if I have a situation like this. If I have a situation like this. So now if I have a circuit like this, some circuit is here. This is point A, this is point B. I have some resistor here, and there is some other resistor here. Now the question is, what is this voltage? This voltage is not necessarily, definitely not equal to this voltage. So V1 and V. So now V1 is not the same as V because there is this extra resistor in there. So we have to make sure that if these two parallel branches are meeting at the same point means this whole thing is the same point. If they are meeting at the same point, then the voltage across one parallel branch would be the same as the voltage across the other parallel branch. So I'm pretty sure you already know this thing, but just to be clear. So basically what I want is, I want the voltage across these terminals A and B. So what is that voltage? That voltage is nothing but the voltage across this 1.2 kilo ohm resistor. But what is the voltage across the 1.2 kilo ohm resistor? That voltage is the product of the current flowing through the resistor times the resistance itself. V is equal to I times R, right? So what is the current flowing through the resistor? That current flowing through the resistor is the supply voltage divided by the total resistance of the circuit. Because this part is not there, so we can forget about this. We just pretend that this doesn't exist because we have open circuited it. So what we have is the voltage, supply voltage divided by the total resistance would be the current. So that supply voltage is 16. The total resistance is 1 kilo ohm plus 1.2 kilo ohms, because we were told that this is 1.2 kilo ohms, this is 1 kilo ohm. So that is the total current. That total current times the load resistance. That total current times the load resistance. So that particular product would give you the load voltage. So that load voltage is 8.73 volts. Okay, so we have now 8.73 volts across the load resistor, but that has to be the same as the voltage across the terminals A and B. So that terminal A and B, I am getting 8.73. But if 8.73 volts is developing across these 2 points, A and B, now let's go back to our circuit and see what is the Zener potential of this diode. The Zener potential of this Zener diode is 10 volts. What it means is that this diode must be reverse biased in a way that this supply voltage, the voltage across the diode, this voltage across the diode is at least 10 volts. Now what I'm getting is only 8.73 volts. So the diode is off. If the diode is off, then that means the diode is open circuited. So whatever circuit diagram I drew here, this is what is actually happening. So even when I plug in the diode, I am not going to see any difference. It's an open circuit. It will remain an open circuit because the diode is not conducting. It has not reached its Zener potential yet. So if the diode is open circuit, then I just have the same network. I don't need to redraw anything. I have the same open circuited network. What is VL now? The first question was, I wanted to find VL. What is VL? VL is the voltage across the load. We have already found it, 8.73. What is VR? The voltage across the resistor, the other resistor, this VR. This VR is just, if you apply KVL, this load, the supply voltage minus the load voltage, VL. The supply voltage minus the load voltage would be VR, right? VI minus VL would be 16 minus 8.73 is 7.27 volts. Okay, so we have 7.27 volts. What is the current IZ? Zener current? Of course, the Zener current has to be 0 because Zener is open circuited. So because the Zener diode is off, we are saying that it's open circuited, and then the current flowing through it has to be 0. Okay, and what is the power dissipated by the Zener diode? That power dissipated would be Vz times Iz is Vz times the current flowing through it is 0, so it's 0 ohms. So we don't care what Vz is, it's just the current is 0, that means power has to be 0. Okay, so no matter what voltage is across 2 points, it doesn't matter. If the current flowing through it is 0, then the power would have to be 0. Okay, so this is your analysis for the situation where you have this particular diode. So this diode, this is not acting as a voltage regulator at all. I mean, whatever I am supplying at the input, that is being scaled by the receiver, being scaled by the resistors, and at the output I am getting some voltage. That's all. The Zener diode is not playing any part. It has got nothing to do. This is not a voltage regulator. This is simply a resistive circuit with a voltage source and the two resistors. Okay. But now, next question is, just do the same thing, but with a load resistance of 3 kilo ohms. So just to make this extra point that I forgot to make, but I made it yesterday. The point is, when you are looking at the Zener diode, the Zener diode is actually operating at this point for our previous example, because this axis, so this axis is the voltage across the diode. So voltage across the diode. So that voltage across the diode was 8.73 volts. So if the voltage across the diode is 8.73 volts, then I am operating in this particular region where I have approximately no current. Actually, I have some very small reverse saturation current. That is we can ignore for most practical purposes. But other than that, I have nothing. Okay, so basically I need to be here. I need to be here to start conducting. So I need to be here or here. I need to make the voltage Vz 10 volts or larger. Then only my diode would conduct. But if I am here operating here at this point with 8.73 volts, there will be no conduction, which means the diode is effectively an open circuit. So now repeat the same example, but with RL is equal to 3 kilo ohms. So you have the same circuit, exactly this circuit, but now I would make this load resistance equal to 3 kilo ohms, and see what will happen. So this is my effective circuit. So my circuit is there. At the first step, I had open circuited the diode, remove the diode and find the try to find the voltage across this open circuit. So using exactly the same pattern, the voltage V would be 16 times 3 divided by 3 plus 1. So exactly the same as before. So that gives me 12 volts. So this V is 12 volts, and that is greater than the Zener potential. So now I am actually operating in this region. So my 12 volts is somewhere here. 12 volts is here. So I am now operating in the on region. So my Zener diode has become on. So if the Zener diode has become on, then what is my equivalent circuit diagram? Because that is what I need to use to actually solve the circuit. The first step, of removing the diode and finding out that voltage across the points A and B, that's just the first step. I just do it in order to see whether the diode is on or off. If the diode is off, then I don't need to draw another circuit, because if the diode is off, this is the circuit. That's open circuited circuit is what you have with the diode on as well. I mean, that doesn't, even after inserting the diode in there. So that's fine. But what if the diode is on? If the diode is on, then you have to draw this particular setup. So you draw this particular circuit. Okay, so the diode, instead now these points A and B, I got it here. Basically A and B, same thing, A and B. So this is also A, also B. So if you have the diode put back in, you would have this particular circuit diagram you saw here. See here. So basically I put the diode back in. So the diode is now acting as a voltage source. So the diode will have a voltage. The voltage would be 10 volts. That's fixed at 10 volts. Because as I mentioned before in our previous classes, the diode, when it reaches the Zener potential, it will stay at the Zener potential even if you increase the reverse bias. So reverse bias, for some value of reverse bias, you reach the Zener potential across the diode. So at that point, the diode will start conducting with very low resistance, and the Zener potential of the diode would appear as the potential difference across the diode. That Zener potential is 10 volts, then it will stay at 10 volts. It will not become 11, 12, 13 volts. Okay, so this is the important thing. So this is where it differs from regular circuit analysis using just resistors. So you have this particular setup. Okay, so now given this particular setup, what do I have for VL, VR, IL, and IR? So what is VL? The VL is the voltage across this load. What would that voltage be? So how do you find that voltage? So any guesses? What is that voltage? So that voltage, as I said a little while ago, so if you have two parallel circuits, what is the voltage? So voltage across these 2 points, would have to be the same as the voltage across these 2 points, right? These are parallelly connected. So now, can somebody tell me what the voltage across the resistor is?
10 volts. So 10
Yes.
volts.
Yes. So always, whenever you have this setup, parallel setup, when you are asked to find some voltage, always see whether what is going on with the other branches, other parallel branches. So in this parallel branch, I am told that the voltage across the Zener diode will not change. It will stay fixed at 10 volts. So if that has to stay fixed at 10 volts, the voltage across the resistor also has to stay fixed at 10 volts. So that is my starting point. From there, I can find out other things. So after that, after I know this, then everything else is very simple, because I now know that the voltage across the resistor is 10 volts. So now I can find out the voltage across this series resistor VR. What is VR? It's just simple KVL. So KVL is VI minus VL is VR. So you have three voltages here, one voltage here, one voltage here, and then one voltage here. So this voltage is, so this is basically the same voltage. So this voltage and this voltage are the same. So if you treat this thing as a black box, this whole thing, this whole side, then what you have is, you have a 16 volts in here, you have some VR in here, and then you have these two terminals A and B, terminal A and B, and that voltage would be 10 volts. VR is just 16 volts minus 10 volts. That is basically from KVL. So KVL says that this particular voltage is 10 volts. The VR is VL minus VI minus VL, which is 16 minus 10 is 6 volts. So if this is 6 volts, then what is IL? Okay, IL, for that you don't need to actually refer to the 6 volt. For IL, all I need to know is what is VL. So VL is 10 volts, I already know. RL, I already know, 3 kilo ohms. Then of course the current flowing through this IL is just VL by RL, right? So this is just basic resistor equation. So VL by RL is 10 volts by 3 kilo ohms, which is 3.3 milliamperes. And what is IR? What current IR is flowing through this circuit? What is IR? This IR is, again, I already know VR. I already know the value of the resistance. So of course the voltage by the resistance would be IR. So the voltage is 6 volts. We had already found it here, right here. So this VR divided by IR is just 6 milliamperes. So 6 volt by 1 kilo ohm is 6 milliamperes. So the last thing to find out, not the last, second last thing to find out is IZ. So what is IZ? What is the Zener current here? How do you find the Zener current? So we know IL, we know IR. So how do we find IZ? What would we apply?
KCL.
Yes, perfect. So basically, I would just do KCL. So I know that the current flowing into this terminal is IR. Current flowing out of the terminal is IL and IZ. So basically, IR has to be equal to IL plus IZ. So this is KCL. So if I have KCL, apply KCL, then I see that IZ is IR minus IL, which is 6 milliampere minus 3.3 milliamperes at 2.67 milliamperes. And what is the power dissipated by the diode? That power is the current times the voltage through the Zener diode. So the Zener voltage is fixed at 10 volts. So that point, so once we determine that the Zener diode is on, then you can blindly say that the Zener voltage is fixed at 10 volts. So that thing we don't change. Then we just found out what the current through the Zener diode is. That's the Zener current was 2.67 milliamperes. So basically the power is 10 times the voltage across the Zener diode times the current flowing through the Zener diode. So 10 times 2.67 is 26.7 millivolts. So this is how you solve these circuits. So this is actually very simple. You take the original circuit, remove the Zener diode, see what voltage is developing across the two terminals across the Zener diode. Is that greater than the Zener potential, or is it smaller than the Zener potential? If it's greater than the Zener potential, then I have a situation where the Zener diode is conducting. So if the Zener diode is conducting, then I don't know what current is flowing through it, but I know for sure that the voltage across the Zener diode is 10, whatever the Zener potential is, 10 volts in this case. So with that knowledge, I can solve the rest of the circuit. So if I know that, I immediately know what is the voltage across the load. If I know the voltage across the load, then I know what the current across the load is. If I know the voltage across the load, I also know what the current, what is the voltage across the resistor, series resistor R, that 1 kilo ohm resistor. So that also I know. So I know all these things. I know all the currents. I know all the voltages. So I can solve. I can answer any question on this on this particular voltage regulator circuit. So basically, this is how you would solve such a circuit. So now, next question is, so before that, let's make this observation. So we had the same circuit, we solved it for two situations. In one case, RL, the load resistance was 1.2 kilo ohms. In the other situation, the RL load resistance was 3 kilo ohms. Everything else in the circuit remained the same. So under that, what did we see? I mean, based on that, what did we see? We saw that when the load resistance was 1.2 kilo ohms, the voltage regulator was not working because the Zener diode was not even switched on. But as soon as I made the load resistance equal to 3 kilo ohms, then suddenly the Zener diode started conducting. So it started acting exactly as intended. So what I had was a Zener voltage V 10 volts developing across the Zener diode, and that voltage showed up across my load as well. So I have a nice voltage regulator circuit that is giving me a 10 volts output. So if I take this voltage 16 volts, so if I take this 16 volt voltage and let's say I make it 20 volts. Let's say I make it 20 volts. So in 20 volts, without solving the circuit, can you tell me what is the load voltage? Without doing anything, without solving anything. So if I make VI is 20 volts, what would be the load voltage?
10 volts.
10 volts, exactly. So the point is, if I increase the load voltage, it is easy to see that if I increase the load voltage, this particular parameter V, that open circuit condition, so when you remove the diode and you calculate V, that V can only increase, it cannot decrease. So if V can increase, then your Zener diode will always be on the on state. So if it's in the on state, then it's always giving me this particular voltage of 10 volts across the load resistance, because the Zener potential is what I get at the output of the load. So that is the principle of operation. So this is the principle. So if I make VI too small, then there is a problem. So for everything remaining fixed, load resistance is fixed, the other R resistance is fixed, everything is fixed. The Zener diode is the same Zener diode I'm using. If the supply voltage is below some value, then at some point I don't have enough potential to drive the Zener diode into the on region. So at that point, my thing is not working. But once I exceed that voltage, I would see that the Zener diode started working. And at that point, if I further increase the voltage, no problem. It will still remain the same. The Zener output will still remain the same. So this is the principle of operation. So basically, we have seen two things. One is, if I change the load, at some point the Zener diode will stop working. I mean, the Zener diode will stop conducting and the voltage regulator will not work as intended. So the load voltage, and we saw that the smaller load voltages, smaller load voltage led to that condition where the Zener diode was off, whereas a larger load voltage led to a situation where the Zener diode was on. So essentially what we want to do is we want to have a large enough resistance. So let's discuss it. So what is the range of resistances, allowable resistances? So suppose our VI is fixed, suppose that our input is fixed. Then how do I know what is the minimum allowed load resistance and maximum allowed load resistance? So for that, start out with the exact same analysis, no difference. You take the original Zener circuit, Zener diode voltage regulator circuit. Now, first, you do this thing exactly as before. You open circuit, remove the diode, you find out what is the voltage developing. What is that voltage developing? That voltage is, as before, VI times RL by R plus RL. We have already discussed this before today. So now what do we want? We want actually this thing. We want this voltage V to be greater than the Zener potential. Otherwise, the Zener diode will not turn on and will not supply this constant VZ voltage. So how do we ensure that? If I want this voltage V, if this voltage has to be greater than VZ, that means VI RL by R plus RL, this term should be greater than VZ. But if it's greater than VZ, then you can solve this inequality and you'll see that VI RL is greater than VZ RL plus VZ RL, and then I solve this, and eventually I find that RL, this value RL should be greater than RVZ divided by VI minus VZ. So this is the situation. So for all values of RL, that is greater than RVZ by VI minus VZ. So if I can satisfy this equation, then the Zener diode will always be on. So I will always get that particular Zener voltage, and this all came from this initial reasoning that I want a voltage greater than the Zener potential across the Zener diode. So this is my this is the way I analyze this. So I found out that RL should be, RL can have any value as long as it's greater than this particular expression, RVZ by VI minus VZ. So what is the minimum value of RL that's possible? That's just RVZ by VI minus VZ. So R has to be at least as large as RVZ by VI minus VZ. So that is RL min. So that RL min is the minimum resistance that's allowed. If you go below that, then your circuit will not work as intended. So this is one. So when I'm actually designing the circuit, I should be able to tell the for example, the user that whatever load resistance you supply to this, whatever load resistance you connect to this voltage regulator, make sure that this load resistance is greater than this particular value, assuming I know what the value of VI is. So in many cases, VI is known. So you already know that I am probably plugging this into some sort of an inverter. So I know what the output voltage of that inverter is. I'm going to plug it into some sort of a power supply where I know what the power supply is going to be, at least for an approximate level. So with all that, I can just say that I can go ahead and say that please use a resistor which is a minimum resistance of this much. You can go above that, but do not come below that. Now you can go above that, but there is a limit. We will see that again as well. But let's so basically this is the minimum resistance. And what is the okay? So before that, just make this point. So we made this point that if RL is R min, the main point is that the diode is on, and we get VZ across the load, right? So this is the point. But now let's see if there's a maximum load resistance we should use. Can I just simply go ahead and keep increasing the resistance? Because you tell me that you don't drop below some 500 ohms, let's say. So I could just bring some 5 mega ohm resistor and then start working in there. I mean, plug it in there. Is it okay? Well, to see that, let's first see what is the load current. The load current is IL equal to VL by RL. Okay, so VL by RL. So what is VL? VL is VZ. So VL is the load voltage, is just the Zener voltage, and that divided by RL. Now, when RL is minimum, when I'm using the minimum value of RL, I have the maximum value of IL, right? So the maximum IL I get is VL. The maximum current, maximum IL I get is VZ by RL min. So is this clear? What is the maximum current? So the voltage across the load resistor is fixed, right? So if that is fixed, then just a moment. Okay, so if that is fixed, then if I make RL smaller and smaller, I get more and more current. So if the minimum I can make RL is this RL min, so maximum IL I get is VZ by RL min. Okay, so this is the idea. So yeah, so there's this question from Vishal. So if IZ is cross maximum Zener current, then also we get VL by VZ. Yeah, I mean, there at that point, actually, some unpredictable things happen, because if you make the Zener current too large, then the Zener can break down in some other way. I mean, I'm not talking about the Zener breakdown or the avalanche breakdown. So if you have too much current, then the Zener diode might overheat, and then it just become a short circuit or a complete open circuit. So it's a little hard to say, but it depends on how the Zener diode is constructed. But the point is, if you increase this point, you should increase this value, because if you increase this, I mean, as long as you're below this, you are guaranteed to get this maximum, this VL is equal to VZ. Beyond that, what happens depends on how the diode reacts, to too much current. So if you just plug in too much extreme amount of current, then the current might destroy the diode. So if the diode is destroyed, then either the diode can become open circuited, so it just doesn't work. But if on the other hand, it might also become a short circuit. So sometimes what happens is that if you destroy certain things, they just become shorted, and then they just start carrying up too much current. I mean, you make LZ, the IZ much larger than the I maximum current, you still get conduction, and that conduction is almost like a short circuit. And in that case, if it's a short circuit, then you hardly get any voltage either. So basically it depends on the diode. So the short answer is that it depends on how the diode behaves when you push in too much current. But for proper operation, we need to make sure that we are below that so that the diode is acting properly. It's not getting destroyed. It's supplying the VZ, the exact Zener potential across the across itself. So this is the main, this is the point. But the other thing, what happens when you exceed certain values? It depends on what is. So many diodes will probably be actually able to withstand more current. So what happens with these extra current, excess current is sometimes the power rating of a power rating is much more. So the diode might be able to handle a lot of power. So if we exceed this Imax, then it will still not get destroyed. Its intended operation might get a little shaky. It may not give you the exact operation, but that might still not get destroyed. But in many cases, it might. So if it gets destroyed, then of course we don't know what the voltage across it would be. Sometimes it might just become a short circuit and no voltage. Sometimes it might become an open circuit and totally stop conducting. So it depends. Okay. But yeah, so as long as we are there, we are in the proper range. So within that range, let's suppose we have found out some RL min. So what is the RL min? We found out according to the description before. So from there, I can find out what is the maximum amount of current that might be flowing in there. Okay, so for this, you could just, sorry. So this IL min, this will give you the maximum value of the current. So you could just do the same example here. So you can take this example and see what is the minimum current, what is the maximum current. So for this particular example, the two numerical examples we did was for two different values of RL. So from here, you could easily tell what is the minimum value of RL acceptable for this particular network. And that RL min is just R VZ by VI minus VZ. What is VZ? VZ is 10. What is VI? VI is 16 volts. VZ again 10. And then R is 1 kilo. So based on that, I can easily tell what RL min should be. So this is the minimum amount of resistance I can use. Then the next question is, does this voltage VR depend on RL? This voltage, what is VR? VR is this. So VR is this thing. This voltage VR. So if I put an ohmmeter in there, will this VR change as I change the value of the load resistance? Well, it does not, as long as the diode is on. If the diode is not on, then yes, of course it does. You already know this is just standard electrical circuits. But if the diode is on, so we have this almost like a short of a good conductor to the diode and a voltage drop of 10 volts. So in that situation, it does not. Why does it depend on that? Because from KVL we know that. So from KVL we know that VR is nothing but VI minus VL. So if you go back to the circuit, so what we had was, so we had this input VI, we had this VR, then we had some, that is Zener diode, so it was this VZ. So this same VZ appeared across the load as well. So VR, okay, so this is what we had. So what is VR? VR is, you just supply KVL in either this loop or on the outer loop. So let's take this loop and subdue a KVL. So then VR is just VI minus VZ. So VR is VI minus VZ because the diode is conducting. Then there is no dependence on the load. So no matter what load you use, as long as you are able to keep the diode on, keep the Zener diode on, then the voltage across VR is just fixed at VI minus VZ. So it will not change with the load. So that means that the current through IR, the current through the resistor R is also fixed, because if, what is the voltage? Now, what is the current? The current through the resistor is VR by R. So when I say resistor, I mean this. I mean this resistor, the current through this resistor, so this IR. This IR is fixed, right? So this IR is fixed VR divided by R. So this is IR. We have IR. Fine. So now IR is fixed. So what is the Zener current now? The Zener current, as before we have seen from KCL. So the Zener current is this Zener current, so IZ, and then we have IL. So the current IZ is IR minus IL. So IZ is IR minus IL. So IR came in from this way. If you look at this terminal, IZ went this way, and L1 came this way. So IR is equal to IL minus, IZ is equal to total current coming in and the rest of the current that's leaving. So IR minus IL is IZ. So IR minus IL is IZ. So when is IZ maximum? IZ will be maximum when IL is minimum. When IZ is minimum, when IL is maximum. So from there, I know what is the maximum and minimum Zener current. But now, what is the minimum Zener current? What is the minimum? So what is the minimum load current? How do I find the minimum load current? The minimum load current is just the current that you get from this condition. What is the minimum? IL is minimum when IZ is maximum. What is maximum IZ? I know that's given in the data sheet, IZM. So if IZM is there, so I can just write down ILM is IR minus IZM. So the maximum load resistance, RL max would be VZ divided by IL min. So this, I hope this makes sense. The voltage, so the voltage, this is the load, RL, this is VL, and then I had some VZ here. So then there is this rest of the circuit. So I know that VL is just VZ, right? So the voltage RL is just VZ by, or maybe write it down VL by I. But VL is just VZ, so VL by I. So if I make IL the minimum, so I put VZ to IL minimum, then I get the maximum possible value of the load. So the maximum possible value of the load is VZ by IL minimum. And the minimum value of the load has to be RVZ by VI minus VZ. So why, so this part, RL min, what is the significance of RL min? Why do I need to not go down RL min? I should not go below RL minimum because if I do that, my circuit will not conduct. My Zener diode will be off and it will not conduct. So my circuit will not behave as intended. And why should I not go above RL max? Because if I go above RL max, the Zener diode will be in the conduction region. It will be above Zener potential, but it will be conducting so much current that that current might exceed the maximum current rating of IZM. So the maximum Zener current might be exceeded. So basically, this thing shouldn't exceed this. So basically the point is, we shouldn't exceed RL min, should be RL max in order to avoid making the Zener current greater than IZM. So this is the case. And why shouldn't we not go below RL max? So shouldn't go below RL min in order to ensure that the Zener diode is on. Zener diode is on. Okay. So basically, we have these two situations. We should not go below RL min, because if I do, my Zener diode will be off and the circuit will not work as intended. And I should not exceed RL max, because if I exceed RL max, if I use a load resistance greater than RL max, then my Zener diode would be conducting so much current that it will exceed the maximum current rating. So this is why I have these two situations. Okay. So is this clear up to this point, this description? So hopefully it's clear. So if you have any question, ask me. So let's do an example again. So take this circuit. I have some 50 volt VI and there's a 1 kilo ohm resistor in here, series resistor. Then I have this particular thing, this VZ of 10 volts, so exactly the same VZ. and IZM, the maximum current this diode can support is 32 milliamperes. So that's given. So this will be given in the equation, or in real life, you'll be getting these things from the data sheet of the diode. So you have all these things, and then you have a resistor, and the load resistor is variable. So I can change the load resistor. So I need to see what are the maximum and minimum values of RL and IL I would encounter. So that is what I want. And the second question is determine the maximum wattage rating of the diode. So what is the maximum wattage rating? First of all, let's deal with question B first. So what is the maximum wattage rating? Maximum wattage rating is nothing but it's a fancy way of saying what is the maximum amount of power the diode can handle. So what is that maximum amount of power? That maximum amount of power is the diode voltage times the maximum current, because diode voltage is constant, 10 volts. So all we can change is the current. So if I increase the current and reach this peak, reach the maximum of 32 milliamperes, then I am going to get a voltage of, so I am going to get a power of 32 milliamperes times 10 volts, which is 320 milliwatts. So that maximum wattage rating is easy. The question is the rest. Determine the range of RL and IL that will result in VL being maintained at 10 volts. So we need to do exactly the same analysis there. So what is the minimum value of RL that I can use? What is the minimum load resistance I can use so that the diode will be turned on? And if we go back to our previous derivation, we saw that that particular RL min is RVZ divided by VI minus VZ. So let's see where that was to remind ourselves. Here it is. So the maximum, minimum allowed RL, the minimum value of the load resistance should be RVZ by VI minus VZ. So this is exactly what I have written here. So RVZ is, R is 1 kilo ohm, VZ is 10 volts, VI is 50 volts. So I substitute these values and I get 250 ohms here. Now what if RL is less than 250 ohms? If the RL is below 250 ohms, then the diode will be off. So my circuit will not work. Circuit will give some weird result. So basically this is why we should make sure that RL is above 250 ohms. Now what is the voltage across R when I am when the diode is on? So the voltage across R when the diode is on, R is this thing. R, we have done it many times. We want to find VR. VR is nothing but from KVL we know that it's VI minus VZ. So VI minus VZ is 50 minus 10 is 40 volts. What is the current? Current to the resistor? The current is VR by the resistance R. R is 1 kilo, VR is 40 volts. So I have 40 milliampere current flowing through it. And what is the minimum load current? What is the minimum value of the load current you get? Load current means the current flowing through the load, IL. So what is the value of IL? You get IL when this is maximum. So the minimum load current is IR minus IZM. So what is IR? IR is IR we just found 40 milliamperes. And what is IZM? IZM is the maximum current supported by this Zener diode. So IZM is 32 milliamperes given in the equation. IR is 40 milliamperes we just found out. So the difference is 8 milliamperes. So again, to remind you what we are doing, I want to find out IR. So I want to find out the minimum of this current. So what is the minimum? So what is the minimum? Of course, I know that IL is equal to IR minus IZ. IR minus IZ. So of course, IR is fixed. So but IZ can change. So if I can make IZ equal to the maximum value, then I will get the minimum value of IL. So this is what we do. So IL minimum is IR minus the maximum amount of the Zener current, and that's 40 by 32 is 8 milliampere. So what is the maximum value of RL max? Well, RL max is the resistor that resistance value that corresponds to that minimum current, and that minimum current is 8 milliamperes. Voltage across the resistor is VZ, the Zener potential, as we have already seen. So this thing is very crucial. So always this thing you should etch it into your mind. The voltage across the load will always be equal to the Zener voltage as long as the diode is on. So if that is, you know these things, then it's very simple. So the VZ by the minimum current is the maximum resistance. So 1.25 kilo ohms. So what it means is that this RL, the load resistance, should be above 250 ohms in order to make sure that the diode is on, and it should be below 1.25 kilo ohms in order to make sure that the in order to make sure that the diode does not exceed its maximum current rating. So this is what your Zener diode, this is why your Zener diode, this is when your Zener diode would act properly as a voltage regulator. So this is how you do this analysis. So when you're actually designing the system, you will do this analysis and you will tell the customer that whatever you are free to plug in any load resistance, but just make sure that it does not fall below 250 ohms and it does not go above 125 kilo ohms, 1.25 kilo ohms. So this is the general idea. So any questions on the concept and the problems we solved? Okay. So now finally one other thing. Here we assume that the voltage is fixed. The voltage is fixed at some value. Here it was 50 volts, before it was 16 volts. And the value of the resistance was, the load resistance would vary. Now let's suppose that the variable, the RL is fixed, load resistance is fixed. I know what the load resistance is, but the variable, the VI is variable. The input voltage can take different values. So sometimes I may be supplying 15 volts, sometimes I may be supplying 16 volts, sometimes I may be supplying 20 volts. So what is the minimum and maximum voltage we want? So the point first of all is, as before, we want VI to be large enough so that it can turn the diode on. So that's the most important thing, because if VI is not large enough, so if you have your VI here, you have this, you have this Zener diode. So the first step is always to make sure that I have a voltage large enough across the Zener diode in order to turn that diode on. So this is V, this is R, this is RL, okay, and this is some VZ. So what I want to ensure is that this voltage across the diode, if you remove the diode, whatever voltage you get across the two terminals that would eventually be connected to the diode is greater than greater than the barrier, the Zener potential Vz. So that Vz I'll be given, but also I know that V, this voltage V. So if you remove this part, then you'll have some voltage V developing across the two terminals of the diode. So that voltage, as we have discussed many times so far, you have a voltage V which would be equal to RL times VI by R plus RL, right? So basically, total current flowing through the circuit would be VI by R plus RL, because I have removed the diode. I don't need to care about that. And then that current times the load voltage would be RL. So load voltage, load current, load resistance times that current is the load voltage, but the load voltage is same as the voltage across the two open terminals of the diode. So this is the principle as before. So we have this, and then I want to set this thing, set the value of V, set this thing at least as large as Vz. So I want to make it larger than or equal to Vz. So if I make it greater than or equal to Vz, then I see that, and I solve this equation, I see that Vi will have to be greater than or equal to Vz times R plus RL divided by RL, which means the minimum Vz, minimum value of Vi I should have is at least RL plus R times Vz divided by R. So that is the minimum required voltage. So this is how you find out the minimum required, because if you go below that, you will not have enough voltage to drive the diode into the on state. And then there is the maximum allowed VI as well. And for that, you first, whenever you are trying to find some maximum value, you'll go ahead and see what is the maximum Zener current flowing. The maximum Zener current flowing would be IZM. And of course, for that IZM, there will be some IR and IL. So IR max. So basically, if you write it down, so this is just, so the Zener current is just IR minus IL, right? So that is what we have already established. So what is IR max? IR max is IZM plus IL. So as ZM increases, IR increases as well. So basically, IR max, for IR max, you get some ZM. So IL does not change. So remember, IL is fixed. Again, if you're confused, again, remember the original setup. So you had this V in, Vi, let's suppose. You had this resistor R, you had the Zener diode, Vz with a voltage of Vz, and finally you had this RL, right? So now what is IL? IL is Vz by RL. So assuming the load is assuming that the diode is on. So if IL is Vz by RL, so Vz does not change. So Vz does not change, RL does not change, none of these changes. These are all fixed, which means IL is also fixed. Okay, so this is the principle that IL does not change. So IR max, so if you increase the Zener current, IR max must increase, so there will be some maximum, for maximum value of IR max, I will have the maximum Zener current. So now VI max, what is the maximum value of I max, VI max? What is the maximum VI allowed? That would be the maximum voltage drop across R, the maximum voltage drop across R. So if you increase IR, then if you keep on increasing IR, so this is IR. So if you keep on increasing IR, your IZ will also increase. So at some point, it will reach IZ max, right? So IZM, so maximum value of IZ. So now I want to find out what is the maximum value of load resistance that leads to that situation. What is the maximum value of supply current or supply voltage that leads to that condition? So that condition is led to if you have of supply voltage of VR max by Vz. So you have VR max by plus Vz. What is VR max? VR max is IR max times R. So IR max times R. And Vz is Vz. Nothing changes. So VI max is IR max times R plus Vz. So this is the maximum value of voltage you can supply. So basically we need to make sure that our VI is between these values. So VI min and VI max. So if you go below VI min, then your diode will not be turned on because you will not have enough supply voltage. And if you go above VI max, then too much current will flow through the diode, and then you will also be in trouble. So basically, this is the way you analyze the voltage regulator circuit, and you voltage regulator circuit, and you find out what is the maximum and minimum values of the maximum allowed values of these quantities, the supply voltage, the supply current. So we didn't look at one possible situation where your input and resistor both are variable. So that becomes a little complicated, but it's actually straightforward. I mean, you can look at this and then the conceptually straightforward, although you have to do a lot more, bit more computation. But the point is you need to keep these things such that the current IZ max does not increase. So that will give you the maximum values of certain things. And you want to keep things such that the supply voltage across the diode, Zener diode, is at least as large as the Zener potential. These two things you have to ensure in order to ensure proper operation of the circuit. Okay, so any questions on Zener voltage regulators? Because this concludes our discussion of this topic. Okay, so one other thing. So I hope you have already received these practice problems. So I hope you are looking at those because those are important. We will discuss some few of those. Many of these problems are repetitive in nature, so I'll tell you one or two problems, show you one or two problems, how to solve them. But by that time, over the next week, please make sure that you go through all of this so that by our midsem, you don't have any conceptual difficulty. So you are able to solve all problems in the exam. So that is why I gave you these things. So everything comes from the very simple principles. Everything. So the thing about electronics is that most of these analysis, you just use some very basic approximation to a diode. So everything becomes rather straightforward. You don't really need to worry about many things. You just see whether the diode is forward bias or reverse bias. It's reverse bias, it's open circuit. It's forward bias, it's closed circuit. In a Zener diode, if you have enough reverse bias, then you will reach the Zener potential, then it's conducting something. And in the other situation, you usually don't reach this condition in the other, for the semiconductor diodes, regular semiconductor diodes, you have a very large avalanche region. But if you reach that, then things become different. But the point is that you have all these nice equivalent approximations which you can plug in. You can easily do the analysis and you can find out the desired result. Only thing to keep in mind is whether you should put a voltage drop of 0.7 volts in what direction, for example. So when you're doing a regular diode analysis, that knee voltage, where do you put it? in your second approximation. So these sort of things you will have to
Sir, I think you're muted.
Okay, so sorry, thanks for letting me know. So basically, that's the point. The questions, what I sent you, just go over the questions, see if you have any problems, if you were facing any problems. But I will.
Sir, again you're muted.
Okay, okay. So I will basically discuss some of the problems, and then we can. So then I think you'll be well prepared for. Anyone has gone over the questions? Okay, please do so this weekend. Please, by all means, go through the questions, because otherwise there will be problem in the difficulty in the midterm. But tomorrow, in the next week, I will solve problems, but make sure that you already are familiar with what is expected. Otherwise, you will not be able to follow through it, right? So please think about the problems when you see this, and then we will discuss. Okay? All right. So we will meet next week. Okay. Thank you all.
Thank you, sir.
Thank you, sir.
Thank you, sir.